Imagine falling into a black hole. To the outside world, you never cross the horizon. To you, you cross it and feel nothing until what comes next. Story 1. What your distant friend sees. To someone far from the black hole, your fall looks weird. As you get closer to the event horizon, your signals take longer to reach them. Each hello arrives more delayed than the last, and more redshifted, meaning the light is stretched to lower and lower energy. You appear to slow down and fade. From their perspective, you never quite cross the horizon. You just become dimmer, redder, and harder to detect until you effectively vanish into the background. Important detail, that doesn't mean you're hovering there. It means information can't easily get back out. Story 2. What you experience. For you, the fall is finite. If you jump in, you cross the horizon in a normal amount of your own time. No infinite waiting. No paused on the edge. Locally, you're just in free fall. And the event horizon is not a solid surface. It's a boundary in space-time. Past it, every possible future path points deeper inward. Even light can't choose a route that leads back out. So what actually kills you? Not gravity in general. What kills you are tidal forces, the difference in gravity between your head and your feet. For a stellar mass black hole, the horizon is relatively small. Tidal forces near it can be enormous. Your feet are pulled much harder than your head, stretching you like a noodle while also squeezing you from the sides. This is spaghettification, and yes, it's as unpleasant as it sounds. In that case, you could be torn apart before you even reach the horizon. For a supermassive black hole, the horizon is huge, and the tides at the horizon can be mild. You might cross it intact, with nothing dramatic happening in the moment, but the calm doesn't last. As you fall deeper, tidal forces grow fast. Eventually, you're stretched, squeezed, and ripped apart, long before you reach the center. Here's a wild detail. The time you have after crossing the horizon depends on mass. Roughly speaking, a approximately 10 solar mass black hole gives you milliseconds from horizon to center. A million solar mass black hole gives you about a minute. A billion solar mass monster can give you hours. Still not a fun weekend, but noticeably different. Here's the key rule. Bigger black hole, gentler horizon. Smaller black hole, deadlier horizon. But there's a plot twist. In real life, the horizon is rarely the first problem. Accretion disks, the hot, deadly donut. Many black holes are surrounded by an accretion disk. Gas spiraling in, heated to insane temperatures by friction and gravity. That disk can blast X-rays and gamma rays. If you try to fall in through a bright accretion disk, you'd likely be cooked by radiation and shredded by turbulence long before any clean textbook horizon crossing. The calmest fall would be into a quiet black hole with little surrounding gas. What would you see while falling? As you approach, the black hole's gravity bends light. The universe ahead of you looks distorted, like a funhouse lens made of space-time. Light from behind can be focused into a warped ring around the black hole. This is related to the photon sphere, a region where light can orbit. If there's an accretion disk, it can look lopsided. One side brighter because the gas on that side is moving toward you at relativistic speeds, boosting its light. The other side looks dimmer because it's moving away. Time also gets strange. You might watch the outside universe appear sped up in some directions, because your frame and distant clocks are no longer in sync. Meanwhile, to your distant friend, your clock looks slowed. Both descriptions are consistent, because now is not universal in relativity. And if you tried to hover near the horizon instead of falling, you'd need absurd acceleration that blows up as you get closer. That's another reason free fall feels smooth, but trying to stop gets impossible. Can you fire rockets and escape? Outside the horizon, yes, if you're far enough out and have ridiculous thrust. But close in, gravity wins quickly. Inside the horizon, escape stops being an option in a deeper sense. It's not just hard, it's not a future direction anymore. Can you send a message back? Once you're inside, no, not because your phone loses signal, but because every future-directed path leads inward. You can shine a flashlight outward all you want. The light still moves at light speed, but it can't reach the outside universe. What happens at the center? Classically, the math points to a singularity, a region where density and curvature blow up and our equations stop behaving. Most physicists take that as a sign we're missing a full theory of quantum gravity. We don't know the true microscopic ending. Also, real black holes can spin, and spinning changes the inside story. But the headline remains, after crossing the horizon, the deep interior is unavoidable. So here's the cheat sheet. To distant observers, you freeze, redshift, and fade. To you, you cross the horizon in finite time, possibly without noticing it. The real danger is tidal forces. Small black holes shred you early. Big ones let you pass the horizon first. In reality, the accretion disk and radiation might kill you before the horizon. Past the horizon, there's no path back out. Your future points inward. If this helped, like and subscribe for more fast space explainers. And comment, would you rather fall into a small black hole instantly or a supermassive one slowly?